Hi, it's Jim from maverickstar Observatory. Very good morning to you. Guys, we're going to make a massive impact today on clearing up some misconceptions, and we're going to start with the 400-year sunspot observations. Now, a lot of you have seen this chart, and you've seen the modified chart version of this where they've sliced off the Maunder minimum section and added it to the end of the chart to show what's to come, because what they're saying is by the low solar sunspot numbers we're going to have the same sort of temperature in the future. But I've got to say this. First of all, we're looking at just 400 years of sunspot observations, and I don't really understand why they have added the little ice age in there as they have, because the misconception is that when sunspots drop to an all-time low, like they did in the Maunder minimum for nearly 50 years, say, or 80 years, the temperatures, according to this map, show that we went into an ice age. It's not the case. If we just look at the right hand side map, we can see the medieval warm period, we can see when the Vikings arrived on Greenland, which I mentioned about a week ago, and we can see when the Vikings left their colonisation of Greenland 400 years later. And you can see why they left. When they arrived, they was just down the back of, or just in that period of the medieval warm period. And 450 generations, or 450 years with many generations in that time period, suddenly realised that Greenland wasn't what it was 460 odd years ago, and it was becoming very difficult to colonise Greenland because the temperature wasn't allowing for agriculture. We've seen this many times in the history of our ancestors all over the world. Our climate on this planet is very fluid and it changes, and that's why when you build a city and you spend, like we do today, billions and billions and billions of pounds building infrastructure, supplying logistics to it, getting it all up and running so it can be sustainable for that short period of time, it doesn't last, because nature changes the course of the climate, and as a result it becomes very difficult for that city to sustain itself. We saw this happen, didn't we, only a few weeks ago in Texas, when the temperatures plummeted, the power grid went down excuse me, and 100 million people were affected by that. If that had continued, I guarantee you there would have been a mass exodus of that state. If it was still to this day not surviving with no electricity, the logistics would have been struggling to get in there, and of course, how do you deal with your sanitation, your fresh water, and all those things you need for a city to survive? I've got to say this, and I've said it many times before, cities are artificial settlements that heavily rely on logistics, supplying them, temperate climates to keep them from having disasters like what we saw in Texas. But getting back to the Maunder minimum and the little ice age on the chart of 400 years of sunspot observations, the big misconception is that the little ice age began a lot earlier than what the Maunder minimum did cover. And you can see that on the right hand chart. You can see when the little ice age began, and that was in the 1400s to the 1800s. And you can see that on the Maunder minimum chart, the 400-year sunspot observations, they have fitted in the words the little ice age, and it makes it look like not only did the sunspots, because they was in low numbers or very little numbers, caused the ice age, but the ice age lasted from 1650 to 1700s before the temperature started to increase. Well, this first of all is a 400-year sunspot observations, and it doesn't include temperatures. And second of all, sunspots do not drive the climate. What sunspots do drive are levels of radiation that are inbound, and that is when sunspot activity falls to great lows, then in radiation we see on the other end increases, and I'll show you that. But the main thing here, guys, is the conception that you're being told by a lot of channels on YouTube is obviously this, that the sunspots are driving temperature, and it is impossible for the Maunder minimum to have caused the Little Ice Age, because the Little Ice Age, as you can see on the right hand side, began, you know, nearly 200 years before. And that is what I really wanted to clear up, because you're going to see this being peddled on a lot of even well known channels that still, you know, probably know the truth but want to make, you know, a few bucks out of the Maunder minimum causing, you know, temperature drops, and let them carry on. You know, we deal with the facts here. I think, you know, I would be supported by a lot of scientists for just clearing this up. And, you know, a lot of climatologists already know this information in any case. And I dare say they get a chuckle out of it when they see, you know, people driving the Maunder minimum as the cause of the Little Ice Age, when clearly the Little Ice Age was well underway before the sunspots started to decay into very low numbers. So I hope I've cleared that up for you. So don't get confused with sunspot observations and temperature. What does happen is I'm about to show you, you know, just for evidence and fact's sake, is just show you how sunspots interact with cosmic radiation. So on the very top of the space environment overview, and I know it's 2014 and I would love a more recent one of this to see how we have progressed through solar cycle 24, but you know, despite my best efforts, and I've had some people from our channel that are subscribers search and they've had no luck with the chart. But what we can see is on the top we see the solar cycles. The next column down we see the sunspot numbers, and the next column down we see cosmic rays. And you can see that when we go into a solar minimum, cosmic rays increase. But we've reached a point in time where something dramatically has changed. If we look at solar cycle 23 and 22, during the maximum period, there was enough sunspot activity to push cosmic rays completely away. But when we look at solar cycle 24 during the maximum, we can see there wasn't enough sunspot activity to push it completely away, and that is quite alarming, I think, because if the solar cycles continue to decrease in numbers for the foreseeable future, then cosmic rays are not going to be pushed away, and you know, as a result of that, our climates are going to keep getting worse and worse, and you know, that is going to affect the jet streams. And that brings us to the next part of this video. We're going to have a look at what jet streams should look like and used to look like, and then we're going to have a look at what they look like today. So just before we get into jet streams, if people mention, or you hear the mention of grand solar minimum, what you need to think of straight away is a rise in cosmic radiation. And know that the rise in cosmic radiation affects the jet streams, makes them sluggish and break down, and as a result of that we get climate change on this planet, or unpredictable climate. So that's all you need to associate, as far as I'm concerned, with grand solar minimum in the future. So going on to jet streams, well, we used to enjoy around 30 years a standard model of jet streams. In that we used to have a polar jet stream at 60 degrees north and a subtropical jet stream at 30 degrees north, and then the same on the southern hemisphere. So you know, you'd have your southern hemisphere subtropical jet stream at 30 degrees, and on the southern hemisphere you'd have your polar jet stream at 60 degrees. So 4 jet streams, 2 on the north of or on the northern hemisphere and 2 on the southern hemisphere, and that's where there was at 30 and 60 degrees, both north and south. Let me see if I can find a bit better image than this so that you get a bit more clearer picture. So this is a great image to show us how the jet streams used to look around 30 years ago. You can see the polar jet streams in blue and the subtropical jet streams in red, both over the northern and southern hemisphere. They don't look like this today. I'm going to show you exactly what they look like live today, a little later on in the video. But the reason why they've changed in the last 30 years also correlates with something else that has dramatically changed. So we know that the magnetic poles on our Earth have been migrating since the 1900s. So from the 1900s to 1990, our magnetic poles on our Earth migrated 500 miles over the northern hemisphere in the direction towards Russia. And then from 1990 to 2020, we could also say 2021, they have migrated. That magnetic North Pole has migrated over 1,000 miles. So not only has it accelerated, it's covered more distance in a shorter space of time, and coincidentally or incoincidentally, our jet streams have dramatically changed. Now, with a magnetic pole reversal, we also have a weakening of the magnetosphere, and this will allow more radiation inbound in our upper atmosphere, and it will cause effects where more water vapor basically gets trapped in the jet stream. Therefore the jet streams become super jet streams, very wide, very long, and they snap and fracture. And what we're seeing today is an emerge of the northern or the polar jet stream mixed with the subtropical jet stream, and we're seeing this both over the northern hemisphere and southern hemisphere. And this is what really is setting up the effects for climate change on our planet, and that's why we're getting droughts, severe winter storms and floods, all of which are knocking the agricultural business left and right. We've got real problems with association of this, what's taking place. The cosmic rays are inbound, not just as a result of a weakened magnetosphere, but also we are in a time period of a grand solar minimum. And again, not by coincidence, the last 33 years covers the last 3 solar cycles of diminishing sunspot numbers. So the sunspot numbers over the last 30 years have been dropping off exponentially to today, where we see very few. And we also see on solar cycle 24, during solar maximum, the sun isn't putting out enough activity to even drive down cosmic rays in our solar system. That's due to the shrinkage of the heliosphere. So we're dealing with a couple of problems there. We've got galactic cosmic rays, more so coming into the atmosphere, into the solar system, which are interfering with our upper atmosphere, and we've got a weakened magnetosphere, which is our primary protective field, and again it is allowing cosmic rays into our upper atmosphere, and in turn affecting the jet streams. And I've said that we're not at equilibrium yet, so this is going to continue getting worse as time goes on until we reach that point of equilibrium. Now, I just hope in some respects that I'm right about that 40-degree mark, because the sooner we go through this, the sooner we can come out of it, and our climate can return back to some form of normality. Let's hope that when the magnetic North Pole or the dipole does hit 40 degrees, it does leave the strong field lines and goes into the weak field lines, and therefore goes into a reversal. Because we know we've probably got another 40-50 years from that point until the climate starts to reach some normality again and the jet streams settle down. So before we end the video, let's go and have a look at what the jet streams look like right now. So here we are, live on North School, or there might be a lag of about an hour in the information that gets fed up to it, but what we can see is not what we're supposed to be seeing 30 years ago with regular jet streams at 30 degrees and 60 degrees north, both over the northern and southern hemisphere. You can almost see 3 jet streams there, but they are all interacting with each other, and that means we're bringing hot air from the subtropical regions up to the polar regions, delivering more snow as a result, and then polar regions delivering that Arctic air back down into the subtropical, which delivers rain. So there's 2 of the reasons why we're getting extra winter climate at more severe levels or greater magnitude, and also why we're getting a lot more precipitation in regions that shouldn't normally have that level of rain and as a result, in both cases, it knocks our technology about, which affects cities, and it also affects our agricultural production. Just before I end the video, I'm just going to go around the Earth so you can see, the condition of the jet streams all around the world. And just where is the polar jet stream, the subtropical jet stream in some circumstances? And then we're going to have a quick look over the northern and southern hemispheres. Now, I know the video is out of sync with what I'm talking about, but I think you'll pick up what I'm saying here. So over the northern hemisphere, we can see there is no distinction between polar and subtropical. They both interact with each other. They fragment where they get very wide. Then over the southern hemisphere, we've got a similar case. No distinction between subtropical and polar. And this is exactly what you don't hear on mainstream media. Why is that the case? Okay, let's just get it back round so that we can have a look at the equatorial region, so we can distinguish between the northern hemisphere and the southern hemisphere, and then just go back to an image where we can see the level really of fragmentation of the both polar and subtropical, both over northern and southern hemispheres. So I hope really you did get something out of the video, and I hope we've cleared up a few misconceptions with regards to grand solar minimum. And the reason why I talked about the jet streams is because in the comment section we've had a lot of people ask if we could show them what the jet streams should look like as opposed to what they look like now, and give them an explanation as to why our climates are changing on this planet. And I just want to mention this, guys, the link in the description. Come on, I believe that we're doing a better job than anyone on YouTube at the moment with regards to revealing the truth about our climate on our planet in this day and age. We don't just talk about it. We've got equipment out there in the field, and we're trying to increase that equipment in the field, and the only way we can do that is by you guys supporting. And just as a little special thing, if you want to make a contribution to our observatory, I'll give you a shout out in the next video that we do. I know it's not a lot, but really it is an acknowledgement, if nothing else. And if you are supporting this observatory, you're supporting a beacon of light. Let's just say that there is truth in amongst all this darkness that we're surrounded by right now. So if you could help the observatory out, the links are down there. And if you want to become a patron, that would be great. Okay guys, I'm going to leave it here. You enjoy your Saturday, and as always, look after your loved ones, be safe, and bye for now.